Hello and welcome to this video on the centre of mass, which is part of the Forces and Motion module for OCR A-Level Physics. So in today's lesson we're going to be looking at centre of mass and we're going to try to understand what is meant by the term centre of mass. So if we've been successful and we've learned in this lesson, we should be able to understand what is meant by the centre of mass and the centre of gravity of an object. Understand that the centre of mass and centre of gravity of a uniform regular solid is at its centre, and then finally explain the link between the centre of mass and the centre of gravity and stability. So in today's lesson we're going to be looking at the following part of the OCR A-Level Physics specification: 3.2.3 equilibrium, in particular centre of mass, centre of gravity and experimental determination of the centre of gravity. So the centre of mass is where we assume all the mass and the weight of an object to be concentrated, as shown in the following diagram. Here, if the object has uniform density, we assume the centre of mass to be in the centre of the object. Now the resultant gravitational force on the object, its total weight, will act through a point called the centre of gravity. Now it's much easier to analyse and solve physics problems if we think about the weight of an object acting through its centre of gravity and not a collection of many tiny forces acting throughout the object. So at the centre of mass we draw a vector representing the weight, and this always acts towards the earth, so this is called the line of action. Now on a force or free body diagram, the weight of an object must be drawn at the centre of mass regardless of the object, so as you can see in the following diagram. Now this assumes that all of the mass is at this point, so it means that therefore all the weight is found at this point. So in this particular example, this would be an incorrect force diagram because we are not drawing the weight acting from the centre of mass. This would also be an incorrect diagram, and this would also be an incorrect diagram, but this would be a correct force or free body diagram illustrating the line of action of weight of an object. Now if the centre of mass is at the centre of the object, the forces on either side of it are the same, so the forces are therefore balanced. Now as we assume all of the weight acts through the centre of mass, this means our body is in equilibrium. Therefore at the centre of mass the forces on an object either side of it are balanced. So therefore at the centre of mass the turning forces or moments on the object either side of it are balanced. So this means that at the centre of mass the body will always be balanced. So if your centre of mass and therefore your line of action are inside the object's base, it is balanced. Now if the line of action is inside the base of an object, we can say our object is stable and will not fall over. So in this particular scenario our object is stable, or we could also say the object is in a stable equilibrium. Now this is because the forces and moments act on the object are balanced. Now if the line of action is outside the base of the object is unstable and will fall over. Now this will happen when the object is tilted, so this object is unstable, or we say the object is in an unstable equilibrium. So this happens because the moments are not balanced and there is a resultant moment acting on the object. So the stability of an object links to the position of the centre of mass and the base of the object. The lower the centre of mass or the centre of gravity, the more stable an object will be. And the wider the base of an object, the more stable the object will be. In both cases, this is because it is less likely that the line of action falls outside of the base and produces a resultant moment. So an object will be very stable if it has a low centre of mass or gravity and a wide base, and this is used in many designs such as racing cars. Now if we consider an object in stable equilibrium on a sloped surface, we can consider the following forces acting on the object. We have our normal contact forces for X and Y, the two wheels. We have our weight acting from our centre of mass, and we also have our frictional force acting against the motion. Now we know that in a stable equilibrium, the upward forces must equal the downward forces. So in this case, it will be the two contact forces, Msx and Sy, added together, and that will equal the W cos theta, which is going to be the vertical component of the weight in this particular situation. Now it's also important to note that Sx will be greater than Sy because x is lower than y, so there won't be an equal sized force. But also we know that in the stable equilibrium that the slope up forces will equal the slope down forces. So in this case it will be equal, the friction will be equal to W sine theta, so it will be equal to the horizontal component of the weight in this situation. Now the centre of mass of an object is the point located at the object's average position of all the particles of mass that make up the object. Now the average position of all the particles of mass of an object will be the geometric centre only if the object is symmetrical in 3 dimensions and homogeneous, so it has the same density at all points inside the object. Now for other objects, the centre of mass will not be the geometric centre, and in some cases could even be outside the object itself. Now we must be aware of how to find the centre of mass of different objects. Now there are different ways to find the centre of mass of an object. Now for all objects, the centre of mass is directly below a point where the object can be freely balanced. So an object can be balanced if the pivot is placed at the centre of mass. This happens as the forces and moments are balanced on either side of the centre of mass. It's in equilibrium. So in this situation, a pencil is balanced on a finger. Now we can see straight away our line of action from our centre of gravity, and we can note that the forces and moments on either side of this pivot are equal to the other side. Now as we know that the centre of mass must lie in the same plane as where the object freely balances, the line of action of the weight, or the centre of gravity, is always drawn down from the pivot. Now you can find the centre of mass of a symmetrical object by looking at its symmetry. For a symmetrical object, the centre of mass lies at the point of intersection of the lines of symmetry. Now if we look at this following shape here, we can see our different lines of symmetry in the following diagram, and our centre of mass is at the intersection of these lines. So what you would do is draw in several lines of symmetry in an object, at least 3 or 4, and where they intersect or cross is where the centre of mass is found. Now another way to find the centre of mass of an object is that when an object is suspended and hanging freely in equilibrium, the centre of mass is directly beneath the point of suspension. So in this diagram here, the object is freely hung, and the hanger basket will show this because it is just hanging there in equilibrium. Now the centre of mass must lie somewhere in the plane of the point of suspension, which is shown with our line of action, and it's always drawn where the object is freely hung. So we know our centre of mass must be directly below where an object can hang freely, when an object just hangs with nothing else providing a force. Now to find exactly where the centre of mass of the object is, you must freely hang it from several places and draw a line of action for each and see where they intersect or cross. Now, so to find the centre of mass for an object, you could, for all objects, the centre of mass is directly below a point where an object can be freely balanced. For symmetrical objects, the centre of mass lies at the point of intersection of the lines of symmetry. And finally, when an object is suspended and hanging freely in equilibrium, the centre of mass is directly beneath the point of suspension. So we can use this principle to determine the centre of mass of an irregular shaped object. Now this is useful in the real world as it allows you to understand how objects can be balanced. But this can be difficult in practice with complex 3-dimensional objects, but is easy to do with objects made from card. So the centre of gravity of a thin sheet or lamina of cardboard or metal can be found by suspending it freely from 2 or 3 points, as shown in the following diagram. Small holes are made around the edge of irregularly shaped objects, and a pin is put through one of the holes and held firmly in the clamp and stand so the object can swing freely. A length of string is attached to this pin, and the other end of the string has a heavy mass attached to it. This arrangement is called a plumb line. Now the object will stop swinging when its centre of gravity is vertically below the point of suspension. A line is drawn on the object along the vertical string of the plumb line, and the centre of gravity must lie on this line. Now to find the position of the centre of gravity, the process is repeated with the object suspended from different holes. The centre of gravity will be the point of intersection of the lines drawn on the object. Now you can check that the position of the centre of gravity is correct by removing the card and seeing whether it will balance on a pin or your finger at this point. Now we have a weight because of the force of gravity on the earth on us. So each part of our body, our arms, our legs, our heads, will all experience a force caused by the force of gravity. However, it's much simpler to picture the overall effect of gravity acting at a single point, which is our centre of gravity. So the centre of gravity of an object is defined to be the point where all of the weight of the object may be considered to act. Now for a person standing upright, the centre of gravity is roughly in the middle of the body behind the navel. Now for a sphere, it's at its centre. Now, as mentioned before, it's much easier to solve problems if we simply indicate an object's weight by a single force acting at the centre of gravity, rather than many forces act on each part of the object. Now, for a symmetrical object with a uniform density and a uniform gravitational field, the centre of mass and the centre of weight are in the same position. Now, as an object is made up of identical atoms, each with its own weight, the resultant gravitational force on the object will act through the centre of gravity, which coincides with the centre of mass. So the centre of mass is a point through which any externally applied force will produce linear motion, but not rotational motion. Now, on the Earth, the centre of mass and the centre of gravity for an object should be at the same point. Now, if an object's centre of gravity falls outside the base of the object, as mentioned before, it will topple as a moment is being introduced to the object. So to summarise what we've looked at in today's lesson, we've looked at the centre of mass, the centre of gravity, and the experimental determination of the centre of gravity. So if we've been successful and we've learnt in today's lesson, we should understand what is meant by the centre of mass and centre of gravity of an object. Understand that the centre of mass and centre of gravity of a uniform regular solid is at its centre, and explain the link between the centre of mass and the centre of gravity and stability. So thank you so much for watching this lesson on the centre of mass, which is part of the Forces in Motion module for OCR A-Level Physics. Thank you so much and have a lovely day.